learning objective for this video is to describe vectors, something which we've already touched on in Year 10. Now, physics, it deals with a great many quantities, and some of those have both size and direction. It needs a special mathematical language, the language of vectors, to describe those quantities. This language is also used in engineering, the other sciences, and it's even in common speech. So if you've ever given directions, such as go 5 blocks down the street and then hang a left, you've used the language of vectors. In fact, navigation of any sort is based on vectors, but physics and engineering also need vectors in special ways to explain phenomena involving rotation and magnetic forces, which you'll get into much more in Year 11. In this module, we're just going to focus on that basic language and how we describe a vector. So firstly, we have our scalar quantities. Once again, we've already looked at this in Year 10, and they're the ones that only have a magnitude. This is in contrast to our vector quantities, which have a magnitude and a direction. So vectors follow certain vector rules of combination, which we're definitely going to examine in future modules. Some physical quantities that are vector quantities are displacement, velocity, acceleration, and force. And you'll see many more throughout physics and engineering. So learning the rules of vector combination now is really going to help you greatly in later years. So vectors are drawn diagrammatically as arrows, which we know. But to fully describe a vector, we need 4 criteria. So they're described in terms of a line of action. This is most importantly when we're talking about forces. It's a one-dimensional line on which a vector is acting. You can see right now it doesn't look like a vector yet. We're just talking about a line in which this vector is going to act. It needs a magnitude. Now the magnitude is what defines the size of this vector, and it's usually represented by that length of the arrow, but it can also be labelled. The direction defines the orientation of the line of action. Now, in most physics scenarios, you can calculate this direction, or is given to you. In engineering, quite frequently you have to measure this angle with a protractor. Now, the final criteria to fully describe a vector is the sense. In physics, the term sense isn't actually used. It's sufficient to describe the sense purely with the arrowhead and a direction. In engineering, however, the sense may specifically be asked for. So in this scenario, we would be saying that the sense is up and to the right. So it's basically the arrowhead of an arrow. It's telling you which way along that line of action the force is acting. So when we're talking about direction, there's several ways we can do this, and you need to be familiar with all of them because they're probably all going to come up during your study of physics and engineering. So the first one is the simple compass bearing, and we should all be familiar with a compass and how to get those basic bearings. So in this scenario here, I would be saying that is northeast. If I wanted to be a little bit more specific with this, and maybe it's not on one of those 45-degree angles, in this case it is, but if it wasn't, I'm going to need to be more specific with the angle. So I'm going to give a bearing, which is an angle from the closest direction on the x-axis, either north or south, followed by which the direction angle is taken. So in this case, we're looking at north 45, and it's to the east direction of the north. So it comes out as north 45 degrees east. If I wanted to give this as a true bearing, I now need to go work clockwise from north and find my angle. In this case, it is going to be 45 degrees true north. The other, and probably one of the more common ways to denote direction, particularly when we're talking forces, so in engineering this is going to be the overriding way to do it, but particularly when physics start doing projectiles, you're going to be looking at direction mainly in terms of an angle of inclination or declination. So we're looking at an angle taken from the horizontal. So in this case, we're just going to change our point that we're looking at it from, and we're going to say it's now 45 degrees from the horizontal. Obviously in this case our angles aren't really changing that much because I've chosen that nice 45 degrees. So once again, let's just revisit how we would use and why a vector quantity is important. If we have a little ball here and it's moved 100 meters, it then travels north another 50 meters. If I ask for what the distance that it's traveled, you very easily tell me that it was 150 meters. I said the displacement. Now we're talking about a vector quantity, how far it's moved from its actual origin. You can't give it to me now as a scalar quantity because it's clearly got a direction associated with it. So you would end up telling me that the displacement is 111.8 meters, north 63 degrees east. You can see now it's giving me a lot more information. So most of the problems that we looked at in year 10 acted along a single axis. So for instance, an object pushed across a surface or an object falling. These simple scenarios have forces acting on the objects on the same axis as the motion. In these cases, the positive and negative notation has been adequate to denote direction, and basically the entire magnitude of the force is applied to the object. But forces in real life are not that simple, and that's where we take this to the next level in year 11. So let's take, for example, this trolley sitting on a bench. If we apply a force to it, we can see that the force applied is not on the same axis as the fixed plane of motion, which is on the x-axis, whereas this applied force is on the y-axis. So as a result, this trolley is not going to move. However, if we were to just rotate the applied force, a component of this force now is actually going to be in the same plane as that fixed plane of motion. So we can say that a vector has two components, an x component and a y component. We can resolve it into this and work out how much of this force is applied to the cart's plane of motion. And that's why vectors are really powerful and why they get used so much in physics and engineering. That'll be looked at in a later module. For now, we're just going to work on some simple problems based on our understanding so far of vectors.